Hello, I'm Susie Newhan and I'm going to be taking you through some differentiating and integration of log and e functions. Okay, let's start. First of all, let's just remember how we differentiate functions of functions. You remember that we learned the chain rule because what we've got here is a cube function of a linear function. So the linear function is tucked inside the cubic function. So that's why we call it a function of a function. And as a result, it's a bit trickier to differentiate, but not so tricky. Let's remind ourselves how to do it. So dy by dx. Right, so we treat the brackets as though it's a single x to begin with. So we don't even look inside the brackets to begin with. When we differentiate, we multiply by the power. That's that, and let's just not look what's inside that bracket, and we drop the power by 1. So that's pretty normal differentiation. The only difference is because it's a function of a function, we now need to multiply by the derivative of the inner function. So there's a lot of this multiplying by the derivative. And in fact, in all the differentiations we'll do today, you'll see that we're going to multiply by the derivative. So differentiate it as though it's a single x, do the power thing, and then and only then look inside the brackets and multiply by the derivative, because both functions need to be differentiated. Okay, here's another one, dy by dx. Don't look inside the bracket, multiply by the power. Drop the power by 1, so that now goes to minus 11, which is a smaller number than minus 10, and multiply by the derivative. Bang. Okay, so now we have to go in the opposite direction. We need to integrate. This means that something was differentiated to make this. What was it? We want to go back to the original y. This is like dy by dx, and we need to go back to y. It is the reverse of differentiation. So, actually, I should probably just remind us how we integrate. Let's just do that. So, if we were asked to integrate x to the 4 minus 5x squared plus 3x minus 5x to the minus 10 dx. Let's just remember how we do it. So this is going to equal, what do? We do the opposite. We add 1 to the power and divide by the new power. That means if we now differentiate this, we'll multiply by 5, that will cancel out with this, that will drop to 4, and we'll get back to where we started from. So in order to undo differentiation, we raise the power by 1 and divide by it. This has got an invisible 1, so we're going to raise the power by 1 and divide by it. Raise the power by 1 makes it become minus 9, so it's minus 9, and we always remember the plus c unless there are limits given. And we just tidy that up a bit. Actually, it doesn't really tidy up, so we just leave it as it is. Okay, so integration is about increasing the power by 1 and dividing by it. But what if it's a function of a function? So here, we're going to do the same as we did before. We're going to raise the power by 1. So it's going to be 2x to the 3, just rewriting what's in the brackets, right? Increase the power by 1, divide by it. Now, when we're differentiating functions of functions, we always multiply by the derivative of that inner function. But because we need to do the opposite, something that gets undone by differentiation, we have to divide by the derivative, which means we just tuck it on the bottom. If we now differentiate this, we'll get back to that. We'll multiply by 6, that will cancel out with that, that will drop to 5, and as we're differentiating, we'd have to multiply by the derivative, and that would cancel out with that. Let's do another one. So we don't look inside the brackets. We increase the power by 1, so it's going to become less negative, minus 10, and we divide by the new power. And then, because it's the opposite of differentiation, we divide by the derivative of that inner function. Bang, done. Oops, I've got my C's. Unforgivable mistake. Okay, so that's how we integrate functions of functions, just sort of algebraic functions like that. Let's now look at some ln and some e's. Okay, so let's look at some ln functions. So just a reminder, how do we differentiate y equals ln x? Well, it's one of those we just know, so it's important to remember it. It's 1 over x. So how do we differentiate a function of a function? Now we're looking at a ln function, a log natural function of a cubic function. So how do we do that? Well, in a very similar way to the way we just did those other differentiations. We know dy by dx will be, if we treat what's in the brackets as a single x, it's going to be 1 over that. So we're not looking inside the brackets yet. We're just replicating what we did here, treating that as x, so we just stick it over the bottom. And then what do we always do when we're differentiating by functions of functions? We multiply by the derivative, and it's just the same here. So we'd normally write it as 3x squared minus 4x. We do the multiplication, so it ends up over top of that. Okay, so it looks like a particular pattern. The top is the derivative of the bottom. That's the way ln functions always look after they're differentiated. Let's look at this one. Dy by dx. Don't look inside the brackets. Treat it like an x. So it's 1 over 4x minus 5 plus x4. But as always, we have to multiply by the derivative. So that's minus 20x minus 6 plus 4x to the 3. So we tend to do the multiplication and write 1 over the other. So the top is the differential of the bottom. Let's look at one that's slightly trickier. Let's say y equals 9. Oh no, I'm looking at the wrong one. What was I going to do there? No, I think we finished there actually, sorry. Okay, so that's how we differentiate ln functions. Now let's look at some integration. So this is a pattern we should recognize. If we know the differential of ln x is 1 over x, then we know that the integration of 1 over x is ln x. It's just going backwards. Okay, so that's relatively easy. You're not often going to get asked to do that. But what about here? When you think here, what do we notice? Well, we notice that the top is the derivative of the bottom. So if we notice that, we are streets ahead. So we know, because of the opposite we did, that it is ln 5x3 minus 10x squared. So that's our answer. But we can always check it. Maybe I should check in a different colour. This might be a bit thick. Let's give it a try. So that's the answer. I'm going to put a tick. I hope I haven't made a mistake. It's embarrassing if I did. So let's now check that. So if y equals ln 5x to the 3 minus 10x squared plus c, then what is dy by dx? Well, we know that plus c is going to go away. It has no x term, so it can't be differentiated. So now we go back to what we're doing on the previous page. What's the differential of this? Well, we don't look at the bottom. We just rewrite that function on the bottom. We don't look inside the brackets, and then we multiply it by the derivative. X squared minus 20x x, and then we can write it out as 15x squared, sorry, felt tip's a bit too thick, all over 5x to the 3 minus 10x squared, which is what we started with, so we know we're right. Let's do another one. What's this going to be? This is going to be ln 4x to the 5 minus 2x to the 4 plus c, because what do we notice? We notice at the top is the derivative. So if we now were to differentiate this, (4x to the 5 minus 2x to the 4 plus c dy by dx, what do? We just rewrite what's on the bottom, minus 2x to the 4th. But because it's function of function, we now have to multiply by the derivative, minus 8x to the 3, and we see it's what we started with, so we know we're right. So I will just do one more that's slightly harder, but I think it might be harder than we need. So let's just not spend much time on this. Right, so let's say, have this as an example. What if we were asked to integrate this? All over 6x cubed plus 2x4. And what do we notice? We think, well, this might be one of these ln ones, because look, the top looks a bit like the differential of the bottom. That's 3, 4, 2, 3. So it's sort of credible that it's something like a ln. So let's take a guess, which we can always do. Let's say try y equals, because when we're undoing integration, we always end up with y. Let's say y equals ln 6x cubed plus 2x to the 4. Sometimes we use modulus, but I'm not going to do that. So that's our first guess. We think it's close, but not close enough. Let's try again with differentiating it. Well, when we're differentiating ln of a function, the function just goes to the bottom, and then we multiply by the derivative. 8x cubed 2. So that equals 18x squared plus 8x to the cube, 6x cubed plus 2x4. So there was a plus c there, but then it disappeared there. Okay, so how does that compare with what we wanted? Well, this is twice as big as that. Yeah, the top row is multiplied by 2 here. So really what the answer is, so what this final answer is, it's half of our guess. Yeah, we guessed that. We got very close, but twice, 2 times too big. So the answer must be a half of our first guess. Maybe one more of those. I think this might be more than you need. Squared minus 2x, 4x cubed minus 2x squared dx. So again, we think, oh, it looks like a ln, because look, that's a square, that's a single x, da, da, da. So it's credible. So let's guess. Let's try y equals ln of the bottom plus c. That's our first guess. Let's undo it or differentiate it. So again, it will be 4x cubed minus 2x squared, 1 times the derivative, so I'll just write the derivative over 12x squared minus 4x. The c goes away. So how close did we get? Well, the bottoms are the same, but look, the top, and hence the whole fraction, is 3 times too small. So our answer is 3 times this amount. If we now differentiate that, we'll get back to there. Yeah, so we just noticed that we need to multiply that by 3 to get that equal to that. Okay, so just a couple of minutes now on ease. Okay, so hopefully that's in the window. So again, this is just another result we learn, that the differential of e to the x is e to the x. It's a magic property of e. That's the only thing that differentiates to itself. So how do we do it if instead of x, it is a function of x? So we're now getting to the chain rule, function of functions zone. Well, as we always do with these chain rule-y type questions, we treat it as though it's a single x, so we just rewrite it as that. And then we remember, oh, but it's a function of a function, so I need to multiply by the derivative. How about this one? Well, if I want to differentiate this, I start off by treating it as though it's a single x, so I just rewrite it. You always just rewrite the e. But it's a function of a function, so I have to multiply by the derivative. And there we go. So how about integration? Well, what about if we have to integrate e to the x? What if we have to integrate e to the x squared? And what if we have to integrate e to the 3x to the 4 minus 2x squared dx? Well, we know that e to the x doesn't change when you differentiate it. So it's just that. That's a nice property of e. What do we do with here? Right, it's like those previous integrations of chain rule. So we rewrite it, and but because it is a function of a function, and if we were differentiating it, we would multiply it by the derivative, but now we're going to divide by the derivative. So remember the thing about the power rule. The power rule doesn't apply here because it's e that's raised to a power, and e has special properties. So we don't do the increase the power by 1 and divide by it. We simply recognize that if it was a single x, we would rewrite it, but it's not. It's a function of a function, so we divide by the derivative. And here it's going to be e to the 3x4 minus 2x squared, and we're just going to divide by the derivative. So what's that? 12x to the 3 minus 4x. And finally, let's just make sure that that works. So supposing we wanted to go the other way round and say we wanted to differentiate this. You don't have to do this. This is just proving that it works. Minus 4x. So what do we do when we're differentiating the e function? Well, we certainly just rewrite it. But because we're differentiating a function of a function, we have to multiply by the derivative. But there was already this 12x cubed minus 4x on the bottom, so they just cancel out. So we get back to where we started. So with these ones, we're just dividing by the derivatives. So treat it like a normal e to the x and then divide by it, the derivative. So hopefully that helps. Okay, so here's some questions. I'll reveal the answers in a moment. So here are the answers. Okay, and here's some integration questions. Oops, I've lost them in the integration questions. So these don't all fit on the page, but so hopefully you can freeze the video at that point. And here's the answers. And then here's the ones on the bottom. And there are those answers. Okay, so I hope they help.